Hello everyone. This is a polyhedron, a solid object with all polygonal faces. Now this is made up of multiple flat surfaces like this one, these two, then we have this one and this one. These flat surfaces are called faces. The connecting lines between these faces are called edges. For example, these are the connecting lines here. These are also the connecting lines. All of these are connecting lines and these are called edges. We can say that an edge is a straight line where two faces meet. Lastly, these corners where the edges meet, these are called vertices. A vertex is a point where two or more edges meet. Now, a very interesting fact is that for every polyhedron, there is a relationship between the number of faces, the number of vertices, and the number of edges. And this is given by a formula called Euler's formula or Euler's relation for polyhedron, which is F plus V is equal to E plus 2. Now, F here is the number of faces, V is the number of vertices in the polyhedron, and E is the number of edges in the polyhedron. Let us look at some examples of polyhedrons and verify this relation as well. How about we start with this shape itself? Let us write down the Euler's formula over here. So this is the formula or the relation. Now, we already saw the faces over here. Let's count them. We have these two faces, then this third one, this fourth one, the bottom one, and this fifth one. So number of faces are 5. Let's count the edges. So we have 4 edges on the bottom. Then we have, this is 5th, these two. This is 6, 7, then 8 and 9. So we had 9 edges. And vertices, they're already highlighted. 1, 2, 3, 4, 5 and 6. 6 vertices, right? Okay. Now let us put these values in this relation. 5 faces, 6 vertices, and 9 edges. So we have 5 plus 6, which is 11, and 9 plus 2, which is 11. This verifies the Euler's relation. Now let us move on to some more examples. The first figure here is a cuboid. Now, if we just try to find out the number of faces, we can see that there is one face on the top, one on the bottom, and 4 lateral faces. The front, the back, the left side, and the right side. So total number of faces are 6. Now let us count the edges. So we have 4, 5, 6, 7, 8. And then these 4 ones, 9, 10, 11, and 12. So total 12 edges. Lastly, we need to find the vertices. Let's check the corners. 1, 2, 3, 4. Similarly, 4 on the bottom. So we have 8 vertices. Now let's verify the Euler's relation. 6 faces, 8 vertices, 12 edges. 6 plus 8 is 14 and 12 plus 2 is 14. So verified. Next example we have here is a hexagonal prism. Okay, let's find out the number of faces. So we have one face, this hexagon, second face, this hexagon. Then if we notice that there is one face on the top, this third, this is the fourth one, this is the fifth one at the bottom, which is sixth, one over here between these two vertices and between these two vertices, the one which will connect these. So this is 7 and lastly this one, 8. So 2, one on the top, one on the bottom and 6 more lateral faces. So we have 8 faces. Now let's find out the edges. So I just drawn this hidden edge as well. So now we have 6 for this hexagon and 6 for this hexagon. So total 12 over here. Then between every two connecting vertices, there is an edge, right? Like between these two vertices, then between these two vertices. So let's find out. It will be 1, 2, 3, 4, 5, and 6. So 6 plus 6 over here and 6 over here. Total 18 edges. Lastly, the vertices. 6 for this hexagon and 6 for this hexagon. So total 12 vertices. Now let's put it into the Euler's relation. 8 faces, 12 vertices, 18 edges. 12 plus 8, 20, and this is 20 as well. Let's discuss one last example. This is a square pyramid. Now the number of faces. So one at the bottom, which is a square, that's one face. And then for every edge of the square, there is one triangular face which is connecting at the apex at the top over here. So we have 1, 2, 3rd, and 4th. So 4 of these, so we can say 4 lateral ones, right? And one at the bottom. Total 5 faces. Let's find out the edges. 4 for the square, and then 5, 6, 1 generating from every vertex to the apex. 7 and 8. So 8 edges. And vertices. 4 on the bottom for the square and 1 on the top. So 5 vertices. Let's put in the relation. 5 faces, 5 vertices, 8 edges. 10 is equal to 10. Hence, verified.